Chapter 6, Atmosphere and Ocean Interactions, Part 3. Here we'll look at El Nino and the Southern Oscillation, which involves the equatorial Pacific, also the Walker circulation, which extends around the equator around the globe. We'll look at impacts from El Nino and La Nina situations, and finally we'll look at a longer-term oscillation dubbed the Pacific Decadal Oscillation, which is important for global temperatures. The Walker circulation and the ENSO oscillation. This is basically a coupling of ocean sea surface temperatures, again in the equatorial Pacific, to the atmospheric circulation that surrounds that. Here we're looking at the last El Nino that spun up in 2016, and we're seeing anomalously warm water in the eastern Pacific. This is an anomaly chart looking at sea surface temperature anomaly, so they're not looking at the absolute temperature, they're just looking at how much warmer is it than usual, and you can see this is an El Nino event, which the signature, one of the signatures, is warmer waters in the eastern Pacific and the central Pacific than normal. Typically, we have easterly trade winds running along the equator in the Pacific. Equatorial upwelling can result because the Coriolis force will turn that water to its right in the northern hemisphere, but it will turn that water to its left in the southern hemisphere. So again, Ekman transport to the right with an easterly trade wind in the northern hemisphere, but to the left in the southern hemisphere. This means you're diverging water at the surface, and to replace that water, you must have upwelling to replace it. That upwelling brings cool water, and a tongue of cool water along the eastern Pacific is typically what you'll see during normal conditions. So this is normal conditions looking at a vertical cross-section of the equator. Again, we see strong upwelling as a result of these strong easterly trade winds causing divergence at the surface, replaced by upwelling. This is also pushing a layer of warm water over towards what's called the Western Pacific Warm Pool, or over Indonesia, Australia area. So literally, you're pushing a lot of warm surface water, and this is a place where the warmest surface waters on Earth for this reason. And actually the sea level, it's not shown here, but the sea level is about 1 meter higher in the Western Pacific on average than in the Eastern Pacific because of this piling up of warm water. Now you know that the thermocline is where temperature decreases rapidly as you go in depths, and that thermocline simply gets pushed deeper and deeper because you're piling up warm mixed water at the surface here, and the thermocline gets a lot closer to the surface here, along with some upwelling that brings colder water towards the surface. So here's what it looks like looking at sea surface temperatures. Normal conditions would be, again, Ekman transport to the right, northern hemisphere, south, southern hemisphere. As a result, upwelling, and you can see a cold tongue of water, and that's typical during a normal year scenario. Now we already know from our thermally direct circulations, where you have warm water, you could expect to have low pressure form, and where you have cold water, or any kind of cold surface, you'd expect surface high pressure to form. So as a result, what you have is now converging air over Australia, the Pacific Warm Pool. That air converges, goes up and rises, ends up hitting the troposphere. Some of it goes over towards the Indian Ocean. The part I'm concerned with now is part of it returns the flow across the Pacific Ocean from west to east at height, and then it cools and sinks down over that high at the surface, completing the circulation cell. As a result of all this, again, you get rainy conditions over the warm water pool and very dry conditions, because anytime you have descending air, you're going to have relative humidity lower, and you're going to have dry conditions over the cold water anomaly. At the same time, these are actually linked around the globe, around the equator, in what's known as the Walker circulation. It's certainly worth mentioning that during normal conditions, the Amazon will also have uplift and rain, and subsidence will again prevail on the extreme west coast of South America and the eastern Pacific, again giving you dry conditions in that location. Now, La Nina conditions simply means stronger easterly trade winds than normal. As a result, you can expect stronger divergence of surface water in the eastern Pacific and stronger upwelling than usual, and also a larger pile of warm water extending over towards Indonesia and Australia. The atmosphere certainly reacts to this differential heating across the Pacific by amplifying the convection, the rising air, in the Western Pacific. This amplifies the entire cell. Those easterly trades get faster, that convection gets stronger, that also gives you stronger flow aloft, and also more persistent and stronger subsidence in the eastern Pacific as a result of colder water underneath there. So everything becomes amplified. This is a time where you may see floods over Indonesia as a result of extreme storminess in the western Pacific. It might also be a time where it's extremely dry in the eastern Pacific for the opposite reasons. This whole system has a lot of positive feedbacks in it, as drawn by these arrows connecting different components. So we can start with the easterly surface winds. Let's say they get a little stronger for whatever reason. If they get stronger, the easterly surface ocean currents move more warm water towards the western Pacific. The western Pacific sea surface temperature goes up. As a result, that helps drive deeper western Pacific atmospheric convection, which again will drive the whole cell faster, including the upper level flow from west to east, including the stronger subsidence back to the surface in the eastern Pacific, which will ultimately make the easterly surface winds even faster. And so it continues in a positive feedback direction, stronger and stronger towards La Nina conditions for a period of time. Now here's a map again, just of not anomalies, but normal conditions across the Pacific. Really nice extreme warm pool in the western Pacific, relatively colder in the eastern Pacific, and we're not showing an anomaly now, so it doesn't look blue. However, you can clearly see that the colors are less red in the eastern Pacific than the western Pacific. Upwelling explains many aspects of why ocean temperature in the equatorial Pacific varies from east to west. But what happens if for some reason those easterly trade winds are actually weaker than normal, or in extreme cases may even reverse, meaning going west to east? What you'd expect in that scenario would be less Ekman transport or less divergence in the eastern Pacific than normal with weaker trade winds, so less to maybe no upwelling of cold water there. And warm water could be allowed to slosh back east towards the East Pacific, or in an extreme case, if the winds completely reverse themselves going west to east, they could simply drag it back towards the East Pacific. We'll find that that water actually gets trapped at the equator from Ekman processes. So the sea surface temperatures, if the trade winds die down or if they reverse, would definitely be higher than normal in the eastern Pacific. Here's just kind of looking at the scenario. Here's a typical scenario where there's wind stress along the equator. Again, it does cause some divergence in the eastern Pacific, giving you this cold water, but it also manages to push some water towards the West Pacific just along the equator where there is no Ekman transport, and it pushes it and piles it up. Of course, you guys know now that the pressure gradient force in the ocean works by having higher ocean column heights in some places. So if the water is 1 meter high in the western Pacific than it is in the eastern Pacific, there's a pressure gradient force that wants to move the water towards the lower levels. So there's a balance there between wind stress and pressure gradient force. So if the wind stress dies down, you might expect the pressure gradient force to be able to push water back towards the eastern Pacific and kind of smooth out and kind of give the whole Pacific more warm water than usual. Now, how it gets trapped at the equator and doesn't just spread north and south altogether, a lot of it does spread north or south, but the part that heads towards the east kind of gets trapped at the equator. And this is because any water that tries to move from west to east, let's say this blue line up here in the northern hemisphere, will get turned to its right. And as soon as it finds itself in the southern hemisphere, it gets turned to its left, and so on and so forth. So it ultimately gets trapped as a wave along the equator. You could do the same scenario for water that starts in the southern hemisphere, also gets trapped along the equator due to the differential Coriolis force across the equator. Now this gets somewhat complicated quickly because there's these things called equatorial Kelvin waves, which is really a pulse of energy or a wave that physically gets trapped along the equator and has to travel west to east along the equator. So it's a bulge of sea surface height that propagates from west to east over a period of time. At the same time, there is a little bit of sloshing, there is a little bit of movement in extreme cases of the water itself, in other words, a current that could move a little bit west to east at the same time. This whole sloshing of warm water back towards the East Pacific is one part of why the East Pacific warms when those trade winds weaken. Again, the pressure gradient force gets the force water a little bit towards the eastern side of the ocean. However, the primary reason that the water's warm in the eastern Pacific during weaker trade winds is simply there's less upwelling there than normal. Now here's a very short video looking at the sea surface height anomaly, again, an equatorial Kelvin wave, that once the trade winds weaken can propagate from the West Pacific across towards the Eastern Pacific. And again, we're looking at reds here, which makes you think that it's sea surface temperature, but it's really sea surface height we're looking at here that propagates across. They're almost the same thing here. Anytime you have higher sea surface heights here, it pushes down the thermocline and will give you ultimately warmer water at the surface. So again, weaker trades, you can move warmer water, or at least higher sea surface heights, pushing down, depressing the thermocline in the Eastern Pacific. And what I've been describing here really is El Nino conditions, where you have weaker than normal trades, or in some cases reversed easterly trade winds going west to east. As a result, you have more warm water at the surface than is typical in the Eastern Pacific, weak to no upwelling happening in the Eastern Pacific, and as a result, you have overall just a more consistent warm layer across the Central Pacific in general. Here's looking at the sea level changes as El Nino starts up. Again, typical conditions here in March 97. This is right before one of the strongest El Ninos ever happened. And you can see that nice warm pool over in the Western Pacific, relatively cold in the Eastern Pacific. As time went on, every month here, you again see that warm water trapped at the equator. And now you're seeing warm water spread pretty well across the equator. And in this is one event where the trade winds actually did reverse themselves from west to east, so they really helped drag along that warm water and push it towards the Eastern Pacific. That doesn't necessarily need to happen to have an El Nino. This just happened to be a very strong El Nino where the entire system reversed itself and you ended up with west to east trade winds, an extreme example. And finally in October 97, you see really a good piling up of warm water over here in the Eastern Pacific. And actually what these charts are looking at again is sea surface height, and this sea surface height is indicative of warmer conditions over there in the Eastern Pacific than is normal. Here's actually sea surface temperatures during a strong El Nino, showing exactly how warm the water gets. Compared to usual, there is no cold tongue as you'd expect during normal or La Nina conditions. Tropical sea surface temperatures warmer than normal in the Eastern Pacific during El Nino. Weakening of that upwelling, less cold water than normal, means warmer than normal. As a result of all this, the atmospheric circulation responds as well. Essentially what happens, if that warm water anomaly propagates to the east or moves to the east, the convection follows it. And so the cells above here, these overturning thermally direct circulation cells that exist along the equator, the Walker circulation changes. And in this case, if the warm water is mostly in the center of the Pacific, so is the convection. And now the subsidence moves over into the Amazon region. And so typically what you'll see during a strong El Nino is much less rain in the Amazon than usual. And at the same time, you do not have the convection that you typically have over Indonesia, and they dry out as well. So if you're going to get large tropical forest fires, they're typically going to happen during El Nino conditions where the Indonesian jungles dry out and can start to burn, or where the Amazon dries out and can also start to burn. This has big impacts on global CO2, as we'll see. All right, summarizing the sea surface temperature anomalies that you see during these different modes of ENSO. Normal conditions, you have upwelling in the Eastern Pacific, a nice warm pool in the Western Pacific. La Nina conditions, stronger trade winds, a more pronounced tongue of cold water in the Eastern Pacific that in this case extends to the Central Pacific, and that warm pool gets both warmer but also pushed to the west over Indonesia proper, giving them a good chance to have convective rains and flooding. During El Nino conditions, the water is more widespread along the equatorial Pacific. There is no cold tongue in the Eastern Pacific, so overall your convection moves more towards the Central Pacific, which leads to subsidence along the Amazon, but also less convection than is normal over Indonesia, drying them out as well. What you can see from these maps is that overall during El Nino conditions, there's more warm surface water in general over this huge swath of tropical ocean. This does have an impact on global surface temperatures. In fact, El Nino years are quite warm years in general due to this natural variability. Here's the multivariate ENSO index. It uses winds, pressure, sea surface temperatures, air temperature, and cloudiness to gauge the strength of El Nino versus La Nina states. This goes back to 1950, where you can see a La Nina there. Every La Nina is indicated in blue here, and then El Ninos as reds. And the numbers here on the left are standardized departure, essentially standard deviations away from normal conditions. Here's a very strong El Nino in 1983, and here's that strong one we've been looking at in 1998 as well. Here's the last El Nino we had in 2016, which led to actually California coming more or less out of their drought, at least Northern California, not the extreme southern part of California just yet. What I want to point out with this chart is that it's a typical time series of an unstable system, in that small perturbations are amplified by positive feedbacks in the system. So an unstable time series really doesn't stay too long in one stable condition. It oscillates back and forth between extremes. And this is what this is showing. And this is because the ENSO system has a lot of those positive feedbacks in effect that tries to push it. So the question is, what causes the flip-flops? Where does it change from El Nino to La Nina? And what causes the perturbations? Although we have some information about that. For instance, when you go from a La Nina to an El Nino, there is an equatorial Kelvin wave that can help that along as soon as the trade winds die down a little bit. But the question is, what causes those trade winds that die down a little bit in the first place? What causes those shifts? We don't have that much information about that just yet. Global impacts from El Nino and La Nina. There can be floods and drought. Locally, we showed that Indonesia and Amazon are affected by the two different states, but also globally as well. Tropical cyclones, definitely an impact in the Pacific and also an impact in the Atlantic that we'll look at in a chart here. There's impacts from disease outbreaks, where mosquitoes are vectors for diseases, and they can propagate or thrive in stagnant water pools, which actually could be caused by both floods or droughts. You can imagine a flood leaving a bunch of standard water in places that's stagnant for a while, or at the same time you could dry out bodies of water that had an inlet and an outlet, but now they don't, and they're just a stagnant pool of water. So both cases can produce disease outbreaks by amplifying how many mosquitoes you might have. The fisheries, they need upwelling. This is actually how this was figured out in the first place, is that Peruvian fishermen figured out that during the El Nino years, there wasn't an upwelling off their coast, and the fishery died out. Coral reefs, this is such a propagated signal of warm water that it really changes the distribution of warm water, and coral reefs prefer to have cooler water. We're seeing impacts right now in the Great Barrier Reef from these things. Wildfires in the Amazon and Indonesia, especially during El Nino events, and there's many, many more in the literature. Forecasting El Nino. Sometimes the symptoms show up first in the East Pacific and sometimes in the West Pacific. Again, it's a system with a lot of interconnectedness. In 1982, for example, a September El Nino forecasting conference failed to predict one of the strongest El Ninos ever to occur, that 1983 one, that became quite strong just 2 or 3 weeks after the conference. So it is hard to predict, and obviously we're many years out from 1982, and we're getting better at these things, but they are hard to predict, the flip-flop. Even to this day, it's hard to predict exactly when El Nino or La Nina will develop. The problem is we don't really know what the real trigger is for that switch in the initial trade winds, or in the sea surface temperatures that would drive those trade winds. There's many theories out there, even as far as to go as heating of the seafloor by magma, some kind of distribution in the heating down there that happens. Other theories go into the Himalayan snowpack. Big Himalayan snows might cause a less distribution of sensible heating that occurs there. In other words, most of that solar flux goes into melting the snowpack instead of heating the land surface, and that might have a signal that impacts the trade winds and ultimately starts the chain of events, all those positive feedbacks that flip-flops you from one state to the other. Now, if you look at the sea surface heights in the eastern Pacific during a strong El Nino here in the upper, and in the lower during a strong La Nina, there's a difference of about 30 centimeters or more in sea level between those events. So you can get some flooding, a third of a meter is a lot of water along these coastlines when they have El Nino. Now, for the U.S. in particular, El Nino typically will drive a jet stream that tends to head across Southern California and gives Southern California typically a lot of rainfall. Our last El Nino, however, during 2016, did drive a lot of rainfall for California, but more specifically, Northern California got a lot more rainfall than Southern California. So each El Nino has slightly different impact. During La Nina, however, you have a jet stream that splits a little bit, and you tend to get more storms head over the Pacific Northwest. So these are typically the years where places like the Cascade Mountains might get 8 or 1,000 inches of snow during a very strong La Nina pattern because most of the storms track over that part of the U.S. Now, forecasters know that El Nino gives you a typical pattern of precipitation around the U.S., especially strong El Ninos, which this is shown for, and so long-range forecasting often involves using these El Nino analogs. For example, this one issued in December of 2015 for the following 3 months, they basically said, hey, there's an El Nino coming, and we know what El Nino typically does across the U.S., so we're going to make a forecast based on what it typically does. Did it work out very well? It worked out okay. Each El Nino seems to have different patterns individually. They did the same thing for temperature. Here they're showing their forecast of below average temperature to the south, above to the north, which is typically what we'll see looking at the last 5 strong El Ninos. And did it work out exactly? Not exactly, but it is a decent analog for giving you some idea of what to expect during an El Nino winter. One influence of El Nino that's interesting is how much wind shear is in the atmosphere in the Pacific versus the Atlantic. It turns out during El Nino conditions, again warm, wet conditions over in the eastern Pacific compared to normal, you can get more hurricanes in the eastern Pacific due to that warmth, but also there's less vertical wind shear, changes of wind speed or wind direction with height. Hurricanes don't like wind shear. They form better when it's low. So less wind shear, you could expect to have more hurricanes. And that definitely did happen in the eastern Pacific during 2016. However, in the Atlantic during El Nino, due to connections across the globe due to that large El Nino signal, we typically get stronger vertical wind shear that does not support as many hurricanes during El Nino. This is all flip-flop during a La Nina influence where cooler conditions prevail in the eastern Pacific, more vertical wind shear. You expect fewer hurricanes in the eastern Pacific, but you have less vertical wind shear in the Atlantic, so you expect more hurricanes during a La Nina year. These predictions shown here were for 2016, the hurricane season, which starts around July and extends to November. And so we were coming out of an El Nino, and they used this information and much more to kind of give an estimate of how many hurricanes to expect over here. Specifically what this forecast was for, in the preseason, they were forecasting how many named Atlantic storms there would be. So either a tropical storm or stronger, up to a hurricane state. NOAA said 10 to 16. CSU just gives a single number as a best estimate, 14. ATOC said 7 to 13. This is before the season actually happened. Once we were a couple months into the season and patterns changed a bit, they changed their predictions a little bit, with NOAA saying 12 to 17, CSU 15, and ATOC more in line with NOAA now at 12 to 17. The actual number of named storms that happened during this was about 15. So NOAA did a pretty good job early season, as did CSU. Everybody did a pretty good job once we were into the season. And again, this is 2 months into a maybe 6 or 7 month season, so not so bad for a forecast. So we do get a sense of how El Nino and La Nina can influence the amount of hurricane activity in the Atlantic. The next thing we'll look at is what's called the PDO, or the Pacific Decadal Oscillation. What this is it's detected as warm or cool surface waters in the Pacific Ocean, specifically the North Pacific, north of 20 degrees north. So whereas El Nino, or the ENSO oscillation, you're looking at the equatorial Pacific, here the Pacific Decadal Oscillation is looking at the North Pacific. During a warm phase, the western Pacific cools and the east part warms, so along the coast of California gets warmer than usual. During a cool phase, the opposite pattern occurs, where the east part of the Pacific along California gets colder and the western Pacific gets warmer along Japan. This shifts phases, not like El Nino, which is every 3 to 7 years or so. This shifts phases every 20 to 30 years, so a much longer term oscillation. The first thing to pick out here is this is, again, just like the Mi index we looked at for El Nino. This is the PDO index, looking at reds as the warm phase, blue as the cool phase. But embedded in here is the surface temperature of the globe in black. It has, however, been detrended, meaning they took out the long-term linear rise of temperature we have seen in the last 100 years. They took that trend out, removed that linear trend to give it more of a flat natural variability. And if you look at that, you could see that a lot of the natural variability in global surface temperatures is in pattern with this specific decadal oscillation. So again, they took out the rising trend of temperature, which is related to something else, more specifically the rise of greenhouse gases. So now you can see more clearly what's happening with the natural oscillation. And again, pretty good relationship between the PDO, Pacific Decadal Oscillation, and the global temperature. There should be no surprise there since the Pacific is such a huge chunk of the global surface in the first place. Scientists attribute stronger Pacific trade winds to the PDO's cool phase. So when we're in a cool phase, when again the eastern Pacific gets cooler, the western Pacific gets a little warmer, you tend to have stronger Pacific trade winds in general for that 20 or 30 years. So these can actually mix heat deeper into the ocean, limiting surface warming. So again, that's probably why we're seeing temperatures dive down globally when we're in the cool phase, because we have stronger trade winds that mix a lot of that energy that's in the atmosphere into the ocean, sequestering it. So therefore, surface temperature drops because now the heat's sequestered in the ocean until the trade winds die down, and that heat can come back up to the surface, transferring it to the atmosphere. I just wanted to add this one in since it's more recent, showing that the PDO has actually been in its warm phase for the last couple years. Here's just looking at the pattern of the warm phase PDO. Again, warm along the coast of the United States, going up into the southern part of Alaska, much colder than average in the Pacific to the west. It turns out one impact from this, besides global surface temperatures, is increased biological activity happening during warm phase PDO near Alaska. So up in this area, decent fishing. However, much reduced biological activity where you have these above average sea surface temperatures, less upwelling than in general, and less good fishing along the coast during the warm phase pattern. Thing reverses during the cool phase, where it's really relatively cool sea surface temperatures for 20 or 30 years along the coast of the contiguous US, good fishing. And also up here you get a really high anomalous sea surface temperatures around Alaska, which kind of thwarts their fishing during the cool phase of the PDO. Key points from this talk: the Walker circulation and the El Nino southern oscillation are shifts in the oceanic temps and trade wind direction and strength along the equatorial Pacific. The main signature is in the equatorial Pacific. Local impacts are very pronounced, such as the rainfall patterns around Indonesia and in the Amazon. Global impacts are many, including hurricane activity in the Atlantic and the Pacific basins, floods, droughts locally, but also far from the area of the equatorial Pacific. The positions of the jet streams, especially over the United States, change drastically. Agriculture, therefore, changes globally, but also in the US, and the spread of disease. Like I said, if El Nino can generate floods or droughts in certain parts of the globe, that might help increase the number of mosquitoes there, which could spread disease more easily. The Pacific Decadal Oscillation shifts between its cool and warm phases on average every 20 to 30 years. The main signature is north of 20 degrees north. So this is a North Pacific phenomenon, whereas El Nino or ENSO is more of a tropical phenomenon along the equator. The PDO has a pronounced effect on global average temperatures, and we saw that by removing the overall trend from increasing global temperatures, which has more to do with greenhouse gases than everything else. If you take that rising linear trend out, you can see that the oscillations in global surface temperature map pretty well with the Pacific Decadal Oscillation, and that's because the Pacific is a huge chunk of the global surface, so we'd expect that impact to happen. There are changes in ecosystem productivity in the Northeast Pacific, specifically the U.S. West Coast, California, all the way up to Alaska. That depends on the phase of the PDO.